Good morning, here again for another lovely session of CENG 4412 Steel and Concrete Design. This is going to be the in the video series, and in this particular portion for part A of today's lecture, I'm going to cover sort of a high-level theory of steel connection design. So the last topics of the course are going to be, well, so far we've covered tension member design for steel, and then beams for steel and concrete, and we've also covered columns for steel and concrete. Today I'm going to cover, the remaining topics are going to be related to connection design, and also connection design for steel and slab design for concrete. I just wanted to cover a high-level overview of steel connection design, and so this is going to be sort of connection design theory. In this video, I'm not going to go into the specifics of calculating the strength of elements, but instead what I'm going to do is discuss sort of a high-level overview of the theory therein. All right, so the first thing I want to talk about is shear versus moment connections. Shear versus moment connections. So, broadly speaking, there are two main forms of steel connections. There are shear connections and moment connections. Well, shear. So for shear connections, these are also known as moment connection, or sorry, as pin connections. Pin connections, shear tabs, etc. And these exist, of course, to transmit shear. To transmit shear. Okay, just a second here. Okay, that should work a little better. These exist primarily to transmit shear. Okay, well, that's already recorded, that's fine. To transmit shear. And I will talk about this later in terms of what this means for individual elements. Moment connections these are referred to either shear connections, or sorry, these are referred to either as moment connections or also fixed connections. And of course, they transmit moment. Moment between members. But what does this actually mean? So this is going to be a bit of a review from, say, structural analysis. So shear connections. Shear connections here. Fundamentally, the idea here is that these will not resist rotation at their ends. Not substantially resist rotation at their ends. Member end rotation. So, in other words, if I draw a simply supported beam, for example, if I design a beam as a simply supported beam, what I am doing is I'm assuming that at the ends of this, there are certain connections that are not going to resist rotation. If I apply a load to this, this thing will bend, deflect, just kind of like this. a very simple single curvature type form, and it will just bend in a nice even single curve, and the ends will be free to rotate. The actual angle at the end of the connections will bend freely with the rest of the member. The connections themselves will not be able to resist any kind of end moment. That, of course, is what we mean by a shear connection. Moment connection. A moment connection or moment connections, the end moment, the end rotation is going to be constrained. So I'm going to draw this as a sort of a beam, and then I want to draw this sort of showing how this would look in a frame. The end rotation is restrained. So for example, if I draw a single beam here with fixed connections, well, in terms of a line diagram, it would look like this. Maybe a load here. But then the deflected shape would look something like this. No rotation at the ends, no rotation at the ends, with then some sort of inflection points in the middle, or inflection points here and here. You'd have basically, in this particular case, you'd have concave up, concave down, concave down. You have more than one concavity, more than one area of concavity present along the beam. Again, and this is necessitated by having the fixed connections at either end of the beam. Now, how does this look in a frame, though? Say we had a frame. Say we had a big, heavy frame here, or just some sort of frame. A frame with beams together. A frame with beams, a beam joined into two columns. Imagine I do something like this. Let's say I have two beams connected to two columns, and I apply 2-point loads here and here. What happens to the curvature of each of these things? Well, in the pin connection, no moment is going to be translated to the columns. Instead, the beams are simply going to are simply going to rotate freely, and these aren't going to, and the columns are not going to experience any rotation from those end connections. And same thing with this one here. But what about something with fixed connections? And so maybe for consistency, I should draw some pins here showing that these are pin connections. But what if I have fixed connections? So this is definitely a bit of theory, a bit of a review of the theory from structural analysis. But if I have fixed connections here, if I have a frame with a fixed connection, the moment I apply a fixed connection, what I am assuming is that if, say, this is at a right angle, if this is at a right angle here, and this is at a right angle here, when this thing is going to rotate, in reality, members don't, even columns don't have infinite stiffness. So what instead is going to happen is that these are going to rotate together. So this thing's still going to want to bend down like this here. But you're going to get some sort of behavior like this. And the columns themselves will also go into some sort of bending. And if this was a fixed connection at the ground, they would come back like this, and you would get some sort of behavior like this also if this was a fixed connection at the ground. So both the columns and the beams will be in rotation. They are, the beam here is going to be transmitting moment to the column, and in turn, because we're applying moment to the column will also enter into bending as well. So this is fundamentally the difference between moment and shear connections. This is fundamentally, again, the difference between moment and shear connections. Okay, so how does this connect to braced versus unbraced frames? Braced versus unbraced frames. Well, braced frames will intrinsically rely on moment connections. unbraced frames intrinsically rely on moment connections. Intrinsically on moment connections. The lateral loads of the building, or the structure's lateral loads, are resisted by bending in the columns. By column bending. And as such, the connections need to be able to transmit this moment, any moment that is present. So if you have a building that is undergoing, say, strong lateral loads, or is undergoing a lateral loading, so say you have a few floor slabs like this, with your columns here, and this would be an unbraced frame. You have load like this. The columns fundamentally are going to be going into bending. So I might have a deformed shape, something like this. Something like this, as the columns are directly transmitting lateral load and moment to the foundation. An unbraced frame, a braced frame need not work that way. A braced frame will often rely on diagonal braces, that sort of thing, to transmit load to the foundation. A braced frame doesn't rely on column bending, at least a purely braced frame. Rather, members are directly put into compression and tension to resist lateral load. Members directly enter tension and compression So, for example, if you had a braced frame like this, a couple slabs like this, you would instead have some sort of bracing here, elements here, something like maybe some diagonal braces like this, or maybe a shear wall or something. And when you tried to apply a load this way, if I tried to apply a load this way and shift all this stuff to the right, this member would go into tension, this would go into compression, et cetera, et cetera. And so these braces would either go into compression or tension. And if you had two braces, yeah, for example, we had two braces, two tension members, this one would go into tension, this would not carry anything, et cetera, just as necessary to carry the lateral loads. And the loads reach the foundation through this kind of brace action rather than through column bending. Okay, so how do we actually design moment connections and shear connections? What does this actually look like in terms of connecting elements in steel sections? So the difference between moment and shear connections. Moment versus shear connections will ultimately come down. The difference between these between moment and shear connections comes down to what elements are connected. What elements of a cross-section are fully engaged or connected. So for example, well, first let's review the definition of elements. If you don't recall this. So structural elements, or structural member elements, or section elements. When I say an element of a cross-section, what do you think that means? Do you remember? What does an element of a section mean? Something like the web, right? The web, the flange, that sort of thing, yes. So an element is sort of a rough definition of this might be the individual plates that make up a cross-section. The individual plates. Now, of course, for shapes, we know that these aren't really plates. For hot rolled shapes, these aren't actually literally welded together. You can actually, of course, make built-up shapes directly from cut and welded plate. But we know for hot rolled shapes, they are not literally plates. In fact, they have fillets. So you can clearly see that they're formed as one unit. So they're not literally plates, but in terms of analysis, we can consider them as plates in certain cases. The individual plates that make up a section. So for example, if we look at a W section, initially we might draw a W section just like this, considering how it really is one continuous member. It's not three things welded together, it's actually it is formed together, it's rolled. You start with a billet of steel and you literally form it with rollers, so this is all cut from the same hole, essentially. But that doesn't mean we can't analyze it as if it's a series of plates. So in reality, yes, it's a single continuous whole, but when we define elements, we're going to consider this here and this here. So effectively we have three elements, 1, 2, and 3. We have the top flange, the web, and the bottom flange. And each of these makes up what we consider individual elements. So, but how does this relate to connection design? Well, to consider this, we have to go back to our theory of mechanics of materials. We need to look at beam theory and how different loads are carried within beams. So consider beams here. Moment versus shear. When we look at a W section, if you recall from mechanics of materials and from our earlier discussions, you'll recall, or you'll remember the logic behind why a W section is shaped the way it is. Let's review. Why is a W section built like this? Why do we have a lot of the area far from the centroid? What is the purpose of that? Fundamentally, why is the purpose of that? Why do we have that? To resist more moment. Yes, exactly. A W section is designed, it's fundamentally designed to create the maximum amount of area as far away from the centroid as possible. Moment is resisted by having lots of cross-section far away from the centroid. Far from the centroid. But then, if you remember from mechanics materials in terms of shear, and also in some of our earlier discussions, shear stress is highest right at the centroid. Right at the centroid. More or less, there are some details of that, but generally speaking, it's highest right at the centroid. And bending stress highest at the edges or at the outermost fiber. In outermost fiber. So what this comes down to is that the flanges contribute very little to shear capacity. In fact, when we saw how to calculate the shear capacity for beams, we didn't even consider the flanges. We looked at only the area of the web, including the whole depth. The area of the web was ultimately what determined the shear capacity of a steel section. So the flanges contribute very little to the shear capacity. And web contributes very little to moment capacity. And this, in turn, will provide us with our fundamental assumptions that allow us to design shear and moment connections. So, oftentimes in structural engineering and all forms of engineering, we make design assumptions. We make assumptions that allow us to design things, allow us to simplify complex behavior into something we can actually analyze and design. So common assumptions in steel and concrete design are something like the elastic plastic assumption, where we assume something will have strength linearly up to the elastic limit and then just remain constant from there. Another assumption we used in concrete design was, what did we assume the tensile capacity of concrete was? 0, yes. In reality, concrete does have some small amount of tensile strength, but it's small enough that we just neglect it. And this is the assumption that this is the kind of thing we're going to do when we make shear and moment connections for steel. So design assumptions, these are our fundamental design assumptions. One, the entire, or the shear capacity of the flanges is 0. Two, the moment capacity of the web is 0. So in turn, these produce two things. Basically, that the moment is carried entirely by the flanges, the shear is carried entirely by the web. And this is what allows us to actually design something. This is what allows us to actually produce something useful, to simplify this complex behavior into something we can actually design. Okay, so let's see what I mean by this. Well, how does this actually work mechanically? In other words, in turn from this, the moment connections will connect up the web. Moment connections will connect flanges. Shear connections will connect web. Shear connections will connect web. So let's look into this. Let me give you some details on how this might work. Okay, questions? Okay. So let's consider how I might want to connect a beam to a column. Or when we could also look at this in terms of beam to beam or a beam to girder or something like that. But let's keep it simple right now and look at how I might want to connect a beam to a column. Let's first look at shear connections. How might I form shear connections? Some examples of this. So let's say I want to connect a beam or a column here to a beam. And this is going to continue on down here, this would continue on down here, and this would end here. So if I want to form a shear connection, now we know that the moment connection, the moment capacity, or our assumption is that the moment capacity of a web is essentially 0. So if I only connect up the web, this connection will not be able to transmit any sort of substantial shear, or sorry, any sort of substantial moment. And that's what I want with a shear or a pin connection. Now, is it true that it's actually 0 moment capacity? No, but this is a relative sort of thing. So, like with all things with shear design, or with steel design, this is all going to be, or structural design, this is all based on relative capacity. So yes, if I connect the web up, it's going to have some moment capacity, but compared to the overall moment capacity of this beam, that connection may only be able to transmit that connection. If I only connect up the web with a little shear tab or something, it may only be able to transmit 5% of the overall moment capacity of the full beam. And so at that point, that is essentially a pin connection. It's a matter of relative strength. But how might I do this? So I want to connect up this web to this, I want to connect up the web of this beam to the top flange of this column here. So how might I do this? Well, there's any number of ways. The first thing, so I'm going to need something to connect this, and I'm going to need some sort of plate or something to join this together. So the first thing I could do is just have a very simple plate. Maybe I would go and, this is poor proportioning, I would want to make this a little taller or something like that, but for example, I might come in here, put a plate in, fill it weld this, bolt here, and bolt here. I just apply some combination of bolts and welds to get the job done. That would be one simple way to do it. I could just have a simple, just a literal piece of plate here, a small piece of A36 or something like that, that I'm going to weld up to the column and then bolt up to the, then I would bolt up to the web here. That would be one way to do it. Other ways, and we could also we might need to cope this flange or something, but I'm just going to give you a couple different ideas of how we might connect these. And then I want to discuss how we would design these things and how we would calculate the strength of these things. So I could do a simple plate. This would be a simple plate. We could bolt it to the bolt to beam, and weld to column. Or alternately, another thing we could do, and there are any number of ways we could do this. I'm just going to give you a couple ones. We could use a simple angle clip angle. I could literally use like an L shape, a small section of L shape, and then maybe I bolt it here, maybe I bolt it here, and then maybe I bolt it here and I bolt it here. So this would be a small L shape that I then just bolt to the column and bolt to the beam. I could use, so I would call this a shear tab. I would call this a clip angle. And so we would use just a bit of L shape. And I could bolt to beam and bolt to column. Or you could also do this as welds. So you can really do this with any combination of bolts and welds. Bolt to column and bolt to beam. Or I could also, I could weld to the column and weld to the beam. I could do any combination of the above. So how would I check their capacities? And so this is not meant to be an exhaustive list of the types of shear connections. I'm just giving a couple of very basic examples. And in reality, this is the proportioning on here is all wrong. These would tend to be much taller than they are wide. I'm drawing this just so you can see the individual elements a little bit better. And then it can be difficult to draw these on a tablet-like device here. So anyway, so the proportions on here are a bit weird. It looks like this would be like 8 inches from the column or something like that, which would be a bit much in terms of normal detailing. But anyway, so how would we check this? Design capacity or design calculations. I'll separate this out like this. How would I do this? Well, when you design a connection, as my old steel professor, Dr. Kahutek, said, this is kind of where structural engineers become accountants. And so this is where structural engineers become accountants. This is where you have to start worrying about really checking all of the individual pieces. So a connection is connections are critical because typically, if a steel structure is going to fail, it's going to fail at the connections. Connections are the hardest part of a structure to design. And the way we design these, or the way we calculate this, is really sort of a chain approach. You look at the load path, and you say which of these is what is the capacity of each of the individual elements in this connection. So, how could this thing fail? Well, for shear anyway, one, in this particular case, the beam web capacity, shear capacity, that could fail, including its reduced capacity from having holes in it. 2, the bolts could fail in shear. Bolts fail in shear, could fail in shear. Bolt shear check, I might just say. So in other words, if I apply heavier and heavier, higher and higher and higher loadings to this thing, eventually, imagine if I actually had this beam, I built it, and then I just started stacking steel plate on top of it. I apply more and more and more and more and more weight, or I put a hydraulic ram on it and just apply more and more and more and more force. Eventually, as I apply an arbitrarily high load, something is going to fail. And what is that going to be? Well, I don't know. But one of these things is going to fail. So first, maybe it could be the beam capacity. Maybe the beam's going to fail in shear. 2, maybe the bolts are going to fail in shear. 3, maybe my plate will fail in shear. In shear. 4, the weld. Maybe the weld fails. Or 5, maybe the column fails. And this again, this is where engineers become accountants, because you essentially need to check each and every one of these things. You need to start saying, okay, well, if my connection needs to carry this much shear, what is the shear capacity of the beam here? What is the shear capacity of the bolts? What is the shear capacity of the clip angle here? What is the shear capacity of the weld? And what is the tear-out capacity of the column web? And really, you need to check all of these things, and whichever one of those is the smallest design value, that is the shear capacity of that connection. That is the shear capacity of that connection. Same thing here, this kind of thing. What could happen? 1, the beam could fail in shear, the beam shear capacity. 2, the bolt capacity, bolts in the beam, and this would be a shear failure. 3, the angle shear capacity. 4, the bolts joining, these bolts here joining the clip to the column. And 5, the column itself. And each of these would contribute to the shear capacity of the member, of the connection. Okay, so what about moment connections? How do we form those? Well, we have any number of ways to do this, but the basic idea of moment connections is going to be connecting the flanges. Mobilizing the flanges. So we have a few ways we could do this. So if I have my column here, again, maybe I'll just draw it like this. Now, I will draw, now even though a moment connection is really about connecting up the flanges, I will always draw it also as connecting the web, because it's pretty rare that you're ever going to have a connection that's only a moment connection, not a shear connection. If you're connecting it to carry moment, you're also wanting, you usually don't have, you can have pure shear connections, but it's very rare to have pure moment connections where you're not relying on that to carry any substantial vertical load. So if we ever connect up the flanges, it's either the web or the web and the flanges. It's usually not where we're ever just connecting up the flanges. So if I want to connect up the flanges here, how am I going to do this? Well, there are any number of ways, but let's give a few here. So you're not going to really ever directly connect the beam up to the column. You could, in theory, do that, but that's constructability-wise, that's very difficult to do. So instead, you're always going to rely on you're usually always going to rely on some secondary members. So in other words, yes, you could just directly butt this thing up against the column and weld it up with a full pen weld or something like that, but that's not really practical to do when you consider the requirements of that, the constructability requirements of that. So instead, what you're going to do is you're going to have something like plates at the top, plates at the bottom, etc. So let's say you went ahead and you would go ahead and have your connection here, your web connection. Maybe you have some sort of weld here, bolts here, but then we would also want to connect up the flanges. And so what I would want is, I would want some sort of plate on the top and plate on the bottom. I would want some sort of plate on the top and some sort of plate on the bottom. And these would then be joined up with either a weld. Maybe this is welded here and welded here. This would be more of a weld type connection. And this is welded here, and this is welded here. And we'll go more, this is a very rough description of this, but we'll cover this more when we cover the design of these things. So this would be a weld area here. So how does this work fundamentally, though? How does this connection work? Well, these two top plates, basically what I'm relying on these is, I have, in order to transmit moment, you need two things. You need not only a force, but you need a force separated by a distance. And this overall beam is going to be transmitting some sort of moment. And when I connect it here and here, that weld area provides the capacity to generate two forces, and those two weld areas are separated by a large distance, the depth of the member. Force times distance, I now have moment capacity. And that is fundamentally how you transmit moment. So I could, so again, this will also have, for the moment capacity of this thing, well, one, I would have the weld strength, or one, I would have the moment capacity of the member, beam moment capacity. And when this transmits moments, one of these plates is going to go into compression and the other will go into tension. So for example, if this was positive bending moment, where this thing wanted to bend like this, the top flange here would be in tension and the bottom flange would be in compression. Just basic beam theory here. One plate would then in turn transmit tension would transmit a tensile force to the column here, and one would transmit a compressive force to the column there. Beam moment capacity. Two, the weld capacity. And weld capacity joining joining plates to beam. Three, the plates themselves, usually the tensile capacity. And for the welds or connections, welds connecting the plate to column and the column itself. And this is what a welded connection would look like, a welded moment connection. And I could also look at a bolted moment connection. Bolted moment connection would look something like this. This one I might make out of, I could make this entirely out of angles. So let's say I wanted to make a bolted connection entirely out of angles instead of plates. I might have a set of clip angles connecting up the web here. So I would have this would be an angle iron here, an L shape here, and that would be that might be bolted. No, I promised I'd do this all with bolts. So I would have bolts here, and bolts here. Then I might have another set of angles here at the top and the bottom. And I could have bolts here and bolts here and another angle here. Hopefully they're built better than they're drawn. Set of angles here with bolts here and bolts here. And we would have to check the capacity. The capacity would come down to a few things. One, the beam itself. Two, the bolt strength. Bolts joining beam to angles. Three, the angles themselves. Four, the bolts joining bolts joining the angles to column. And five, the column itself. So what this comes down to is, in order to know how to do this, effectively, a lot of this is based on basic mechanics, materials, and structural analysis theory. You already have almost all the tools you need in order to design these things. You have the theory, you've learned mechanics, materials, you've learned structural analysis, you're experienced with much of this already. The one piece you're missing that we still need to talk about is the capacity of bolts and welds. That's the one thing we haven't talked about, but once you have that, the rest of this is just mechanics and materials. So the downside of this is that there is no easy way out of this. There is no easy way you can just say, oh, where's the equation, plug and chug, throw it in the calculator, and here's my moment capacity of a connection. You cannot do that when you're doing steel connection design. This is one area where you simply can't do that. Instead, what you need to do is you need to go back to your beam theory and say, okay, well, here's a distance, here is a area, here's the capacity. All of this is designed from a very fundamental base principles, base mechanics and materials point of view. Okay, so I think that'll do it for today. I just want to provide a brief introduction to the theory of connection design, and I think I have covered the basics of both steel shear and steel moment design. I will follow up later on with some later videos on the capacity of bolts, but that'll do it for our lecture in class today. If you have any questions, feel free to see me up here, and as always, thank you.